as Diego again said, we will be doing energy conservation, energy work theorem, and I think other than that, we're just doing a couple of exercises like last time. Hopefully you all know me from last lecture, so I don't have to reintroduce myself. Briefly, my name is Aldazar. I'll type that into the chat so that everyone knows how to pronounce it. And the way that I do lectures is that I'll typically use software called Tape, and I'll use that like whiteboard, draw out questions and everything. I do appreciate when the students participate in the in the discussion, and usually we start off the lesson with a little bit of feed, then do exercises. I just wanted to repeat to students who received script. Did you find the scripts used last time? Do you used to that? I hope you also, all of you did. So, quick feedback from you guys. I'm sorry I have to keep muting everybody as they come in. It's unfortunate, but there's a lot of background noise. Also, can you hear me? That's the most important part. I gotta double check that as well. So right now, I get responses. Worst case scenario, we'll just start. I at least get a confirmation you guys can hear me. Sorry, I didn't find that.
So we can hear you.
Oh, okay, thank you. With that, then I believe we can just start with the lecture. Some of you haven't received any notes. You were supposed to receive like a script from Professor Ilya Diego. If that's not the case, I'll double check that again. Okay, so now let me sharing my screen and start off today's lecture with hold on. With energy. Briefly, I'd like to, like I did last time, the abstract understanding of what it means, what is energy, and then from there we can go to more realistic stuff that can apply more to engineering. Desktop tiling. I select, perfect. So hopefully now I can do that. I'm just going to type in the world. Hopefully all of you see that. If not, then we can we have to find a solution. I would also like to keep it doesn't seem like a time that's a little bit stupid. Nope. No check. I'll just live with this for now. Hold on. Sorry for the delays. Not every day. Okay. So what do we understand from energy? When we talk about energy, we can talk about it in a very spiritual sense. I know it's a little bit silly, bear with me. We can talk about energy in a spiritual sense. Usually we'll talk about body, and this body contains some kind of abstract energy that that swirls, right? We'll talk about this within a body, and that this energy can be transferred, it can be almost received in some term, or and for the most part, despite how that might seem, there seems to be in theory something that is transferable, something that that sort of energy from one form to another. What this concept is, what is, it's a little bit difficult to explain to the, it's just something that we for granted. We just call this this property energy, and why it's there. It's usually because it's entrapping, or it's an entrapment of something. We usually refer to entropy or enthalpy in these cases. So the question is, why are we concerned? For exercises we're working on, it's important to be able to describe the forces for and be using this concept of energy, or how we can determine energy, determine the forces and types of energies using this concept of using this abstract concept. Interesting thing is, we usually talk about how, so just as an example, examples on energy, we can talk of heat. Object could be really and the sun can this energy in the form of. We can talk about energy in the form of elasticity. So if we have a spring, then we talk about spring. I know it's a big we can talk about having a form of elastic energy, that the energy that is or the energy that it can be released with zero consequence, meaning that it doesn't change, or that the energy is observed before and after. We can talk about energy in the form of what do you call it? Sorry about. We can talk about energy, or what do you call it? States. That's another one that was a little bit back in the 50s. We could talk about being in a form of wave. In fact, this almost any, I don't know if we have literally do, but we can describe this form of energy wave. That one of which, of course, is photonic energy. So again, this is just theory. This is just forming the material coming later. We'll simplify it later on. So if anybody's all this in the examination, we can talk about photonic, refer to the photons of light, and even use Planck's equation to, or Planck's equation to determine what that energy is based off wavelength. Trias möchte Frage begin. Oh, you can comment apparently. Oh, I do that. Trit, for some reason you are now partially in control. I have no idea what to do exactly. Maybe I should. That's a really difficult. Hold on 1 second. Ah, there's the chat. Finally. Tip, so do you? Okay. Oh, sure. I could call. I'm not sure. One of the. However, we can talk about. Oops. And relevant for examination, we can determine using a wavelength. We can talk about energy in the form of something that is particulate, meaning particle, or we can talk energy in the form of wave. And for this lecture, we're going to energy in the form of particulates. So we'll more particulate system, And when discussing is, or I not one, need to turn that off. I think what a system is. A system, this is the most important part when discussing energy, can be anything we define. A system can be a single particle. So before we start our exercises and determine energy, what is by this body or system, we have to first determine what is or how to define a system exactly. I have written down here somewhere a definition for system is, hold on, my notes very quickly. But we can start off by saying, actually more system is anything that we define and the boundaries which separate that system from the universe. That's a little too poetic, but in fact that is the case. So we are observing, we've done this before, when we looked at physical systems, what we do is we ignore everything around that physical system to draw a boundary, and in this case, in this current case, we can say, for example, this is our system. We can also, typically we do this, we can turn it into a part, into a single, or we can turn a whole into the simplified, abstracted enough that it's not referred because there's a lot of variations in that system, but we can technically take this and call it our new system, such that the boundary around this becomes our system, even though we're working with two objects containing two varying levels of whatever energy we're observing. It can be a region of space, so it doesn't necessarily have to be just these two particles. We can, for example, if we want to be so bold, that's not what I want to do. Take any region of space around, where are you? I lost you. There you go. Oh, what is that? Interesting. We can take any region of space. Let's say, for example, and I don't mean literal space. I know it's black, but I mean space as in any area or volume around the system, and we can call that whole thing our system. So whatever is outside of this boundary is the universe, and whatever inside this boundary is, or whatever is inside this boundary is our system. And finally, we can talk about a system that isn't rigid, a non-rigid system. What is a non-rigid system? The best way I describe it without opening up some continuum mechanics is, for example, let's assume that this system that we have is a rubber ball. And because it's a rubber ball, this, as a result, if I squish it, the boundary of my system can extend. So right at the beginning, maybe let me do this more visually. So let's say this is not my system. This is just for reference. I want to show you what I mean. Let's say initially when I took my particulate, sorry about that. Okay, move you down. So when I took the particulate system in the beginning, I realized that the ball that I had a region, or a system, the system's space was contained within the square. However, as the ball expands, because it's a rubber ball and it's elastic, therefore it should also compress a little bit, then this region of mine has extended. So we can define our system by simply the perimeter of whatever particulate we want, so that if the boundary of that system extends or compresses, then we can still justifiably work with that system without contradicting our initial definition. A little bit too abstract, I know, but don't worry, we will be getting into the meat of the physics. If there aren't any questions so far, I'd like to continue and move on from this point, but does everybody understand more or less what a system is when we're talking about energy? Just thumbs up would suffice. In the meantime, we'll look into the next part. If there are also any questions, by the way, just raise your hand and I'll gladly answer them.
In fact, I put something in chat.
For some reason, I can't see it.
Oh, I said that I don't really understand. Please, could you explain again?
Again. Okay, sure. Thank you for muting your mic. Okay. So for some reason, you're the only one who has power over his muting abilities. A system. I don't want to overcomplicate this because I think intuitively you guys know what a system is. Very briefly again, a system can be anything essentially that we define. So far, in systems we've worked with particulate is a single particle, literally. So for example, if we did program, then we would say this is my ball, and on this is a vector. Let's see if I can get this open again. Okay. Right, that's annoying that the function is very slow. Sorry about that. I was hoping it would be a little bit more efficient. Go here. No, doesn't want to work. No. So usually, if we work with a free-body diagram, then this is my particle, and this goes falling, and there's force on this system, and the system. I think I have to put you guys up here. Sorry about. There we go. That this, the important part. That is the important part. That we can particulate system shrink it down to some kind of hole or a little point like that, and work that example. However, with energy, we don't need to work with objects. We can work with called systems, and what that means essentially not constrained to one body or the other. And this is also true for forces applied as so. The first definition energy is a particle. So with a free body. The chat function still just as we did with free programs and other exercises, hopefully also did and you discussed work a little bit. We will revise that today. So the first system that we can define within an energy problem is a particle like this. We can also define a system by more than one particle. So for example, I can have 3 particles and I can say, well, now I want to observe this as my system. Basically, a system is a boundary that we define that separates the thing that we are concerned with and the rest of the universe. So anything what's outside this box over here, I will consider system, and everything inside this box is my system, and everything outside this box is not my system. And there's another way of also working with systems to define the boundaries as something rigid or non-rigid. So, for example, I can say this is the way of my system, and it is rigid. Therefore, if this ball were to inflate, it could not extend beyond this boundary. but I can also define my similar thing, non-rigid, meaning it's elastic, and so if this reaches the boundary, then the boundary will end with the ball, if that makes sense. But that's, again, an example we're probably not going to do you guys to at least be aware the system can extend beyond it can have non-rigid boundaries, and it becomes very important during what do you call it? Mechanics, especially mechanics and FEM analysis or element analysis. But don't way down the road for now. With that, I would to work. If you still have questions, ask me later on, but I don't think the most necessary definition or the most important one for your examination. So here's a group. I'm going to see if you guys still, or you still remember what you took last semester or last season, last month, sorry. So I have an object here. Let's hope that the chat function can message into the chat function, see if it's working. Because if it's not, then I can't ask. Ah, yes. It seems, no, wait. Right click and then yes. Testing, perfect, oh, working, wonderful. Thank you very much. Kiarash, hopefully. If I butcher your name, apologies. So now let's look at an object and the force applied to this object. I want that much larger. Humongous. Put that up to 1. Okay. And this object is being dragged. Hold on a sec. So yeah, this object dragged from here to here over a distance r. Can somebody tell me what the work is? I know it's very simple. Make sure that people are awake. So I have a force applied to the object is moved from point to this point with a constant force F. What is the work done? So you're going to try to start overthinking it. The chat seems to stop working because
I sent something. I don't know if you can see it.
For some reason it's not coming up. Oh no, yes, I just got it from Tirt. I got work is equal to force times distance. I don't know why Mbam yours is not working.
So are you the Gatgeber or moderator?
Just send it to all participants.
Okay.
Please, by the way, everybody, when you're sending a message, just send it to all participants so that everybody can see.
Thank you.
Thank you very much. I'm not the guest.
Okay, that's who I was sending it to.
I understand.
Can you see it now?
Yes, thank you very much. Force times distance direction of the force. Finally, somebody wrote D that I'm going to give you minus because there's no D. I'm not going to be that. But so you all understood that force, I think best definition is force distance traveled in the direction of the force. I think that's the most important Can anybody tell me where force is, if the fork is a scalar or non-scalar term? Somebody's microphone is odd. Work equals force multiplication is true, kind of. Like I said, best definition is that it is the distance multiplied by the force in the same direction. So for example, we have our axes. Maybe build our axes from now, so we don't have to worry about them later. If we look at our axes here, we can see that in the axis there is no force. Force has a direction, that's true, but does work have a direction? That's the question. Or if work, sorry, not if work is scalar, that was the question. But as we can see, the force being up is in the x direction only, and the field here is in relative to that distance, and therefore we can just simply done. I'll write that out, please, just to double check that everybody is aware of this. Times there is another way of solving it. So somebody said it is scalar, very good. And saying scalar, scalar, very good. That's wonderful. So it does not have, it can have a magnitude, but it doesn't have a direction. Note here. So work, so if I say if anybody does this during the exam, right? Oh, shoot. No cussing. Okay. If anybody does this, then we know definitely there's a mistake. That's not the case. Work is equal to force R, and it is a scalar quantity. It can be negative. There can be such a thing as negative work being done, but that's more if you have fixed, or if in your system you've different a direction is positive, negative. Okay. So increase the difficulty exercise. Let's now take this force, and we're going to be about it. I said, you know what? I don't like you. I have a force that is to the center of in this direction. Can anybody tell what the work done is given this new, and just to help you, because I don't hate you. Yeah, we'll just terrible looking theta. Sorry if anybody has tried to draw with a mouse, I understand why my theta looks like it's been mutilated. So somebody said this time use sine f. Agree with that? Ah, cosine. Sorry. Okay. So everybody's saying how the determined work is equal to force times cosine. Cannot wait. I had to read it in terms. Hold on. I just got Greek terms. Greek alphabet. Mathematical symbols. There we go. Just copy. And then time. Does everybody understand that? Why is it that we're getting the cosine? This in regard to what is cosine theta in regards to why is it f times cosine theta? Why is it not f times sine theta? Good that you guys know the answer. The question is, why is this the answer? Maybe you know it intuitively because of so intuitively and say, oh yes, theta times r. But why is it cosine theta? Or f times cosine theta? What component are we interested in? Sine is the force for horizontal. And that's an answer. I wouldn't say answer, but I think I get what you mean. I would like to rephrase that. We are only concerned with the parallel to the direction of the motion. So if we because work is first of all the distance. We know in y direction there is no none because the object has not in the vertical direction. Therefore, what we are concerned with component orthogonal, not orthogonal, parallel to the direction of very good, because if you apply cosine 90, that's a very good point. And why I didn't write in the original definition, I write the vector of f. You can cosine theta, again, because then you always have to fit that direction of motion is horizontal. But let's assume that there's all cases. You put 90 over, you'll get 2. So that does work in this 0 here, you'll get 1, f times r again. There's more than one way of looking at it, but yes, I also like 90 is equal to 0. Not bad. But we have this force slide in direction like this. But if I have my system already defined this, then I have to keep that. So it's not simple to say f times cos theta. But always keep in mind it's to how you define your number. Wait, I have that here. Oh no. I wanted to rotate somebody. What a shame. You won't allow me. Okay. Comfort. But when you apply this cosine theta thing, for example, there was a force that was vertical, and what you're essentially doing is rotating your system that is 90 degrees. That in the horizontal direction is again. Okay, moving on from that, let's try to see if we can't do this exercise. I don't want to start off with a difficult one. But any questions? I think this is very easy, Diego, to you guys. I'm just what you did last at this point. If there are no questions, okay. Let's start with our facts. So I don't think you got any. I think you know this from high school. Trigonometry, yada yada. So then I'm going to delete off with our vacuum exercise. So I have a vacuum cleaner that I purchased. I'm proud of it. But then I realized I had to clean with it, and then I was no longer excited to vacuum clean it anymore. Actually, let's just put that like. These anecdotes are breathtaking. Let's put it like that. And let's create something that looks like takes a while to get this stuff done. I apologize. but it will all make sense. So this is the cleaning. First, okay, and fourth to that. And the angle from here to horizontal line is about 30 degrees. And most importantly, do we need any? I think, yeah, all we would need solving the question, which is work done when I move my vacuum cleaner of, no, not eraser, 3. I think that suffice. I think it's pretty easy to solve as well. So I don't want you guys taking too much time. Okay. Maybe making it about elaborate. But yes, I bought a new cleaner. I started cleaning, realized, oh God, I'm doing a lot of, I was determining what is work I'm actually doing. Every time I drag my vacuum cleaner through constantly. Okay, so some answer. Oh, well, maybe I forgot to mention is that we know that since work is equal to force times R, of which should equal then to newtons times meter, which this is the same as in joules. So keep that in mind, please. Okay, and then interesting answers. Somebody said 7 is 130 newton meter, 994 newton. You guys keep doing that. In the meantime, this question should be pretty much easy. I don't know how to have this thing on the piece. You don't need to write. You can just, it's a fraction. Oh, you mean the calculator? I mean, use a calculator somewhere. You have to convert it to a scientific calculator, I guess. In the meantime, yeah, I'm going to do scalar products. Everybody who can, just please write yes, and then I can determine whether or not we should discuss scalar products at all. I'm hoping most of you do, because Diego did say that we discussed scalar products. So actually, let me rephrase it like this. Did Diego teach you guys scalar products last week? Or last, you know what I mean, last lecture? Is that actually 9 out of, okay. While I'm solving this, please answer the question. Did Diego do scalar products with you guys last week? So I got a couple of answers. One is 175, one is 130, one is 994, 129.9. All of these seem erratic. I don't know why you guys got 259. The answer to the question was what essentially we previously, I'm assuming, is a calculus problem. What could it be? I don't know. So like we had the vacuum across the floor 3 meters, very lazy. I don't want to, I want to know exactly how much I'm working every time I'm dragging this vacuum cleaner. So then we wrote F times, or maybe more specifically, F times R. But in this case, we're not concerned with force because the force in the vertical direction is essentially 0. The force in the x direction is the one that I'm more concerned with. So that becomes x cosine of 30, I'm not mistaken, I think so far, times r, which is equal to e times sine 30 times 3. And of course, they all start shouting at me, sir, you did not write in the unit, and I will apologize immediately. And that's equal to, if calculation is correct, 130 joules. So I 259. Please recheck your work. Really, I did get the right answer, and iterates whether or not did you guys get products with D on the last lecture. Somebody please answer that for me. If not, I can briefly discuss it. If yes, then we can just go straight to done by varying forces. Calculation error, I thought. Maybe let me, if you haven't, I think I'm going to leave the video because you didn't know did it. Oh, somebody's joining. Okay, good. Then I would like, sir, could you? Okay. Sir will briefly discuss. Don't, sir. I'm not a yet, at least I feel too formal for me. Way too formal. Okay. Actually, I'm worried that they didn't catch it. What do you call it? Save this image. Exercise 1. And I will part of the script. So if you guys didn't catch it, I'm going to upload it to the script. I'm going to give you guys later. Okay. Scalar product or dot product, that's the terms that we use to describe vector multiplication. Slash. Because the symbol that we use is a dot. I think that's the more convenient name. So if we have two vectors, and now these are vectors, it's important for me to do here is to make sure that they're bold. They're notated with what we'll call the letter. So right now these characters are bold, and that means two vectors. Okay. Cosine. This is the rudimentary quick. Just have it. The is. Just take it is. Don't think about too much about what it's trying to say. To perform a scalar product, this is that you'll require. So if I give you two vectors, and you know this rule, you know the angle between the two vectors, pretty much ready. Another note here is that this is only possible with vectors of the same unit, meaning that you cannot take a vector of force and multiply it or dot product it or dot multiply it with a vector of electric field. That would be erroneous. You need to make sure that the two vectors that you are scalarly multiplying are of the same species, so to say. So an example of dot product would look like this. F. I know it takes all of this, but I don't. There we go. No, the other one didn't work. Fine. You're going to be like. Okay. There we go. These are two. Call them. Nope. I have to always make it bold again. And B. And we have an L between two vectors, and that is, of course, theta. What we want to with scalar is project the magnitude of B. This is one way of thinking about it. This is why and why the direction doesn't really concern us too much. Oh yeah, by the way, to show where this rule comes from, let me here. If we take a line, this orthogonal here to here. So we have a string going from the head of B to wherever it's A, and that is equal to this. So hopefully this will sense where it's coming from. And what we're doing, we want to essentially the magnitude of magnitude being this one over here. Please note that that the B not that or meaning that they are the magnitudes of the vectors A. So we're taking the projection magnitude of B on A. We want to see how what happens as a result. To multiply two vectors scalarly with each other. That means, for example, mathematicians who talk about this course want to find a way to essentially the same thing that they do with numbers like 2 times 3. But we'll say, okay, I will take this vector and go to this vector, the origin, and I want to take that magnitude of this one vector and project it onto the other vector. That's one way of thinking about scale. And this is actually what we're doing, and why maybe they'll start to maybe see a relationship between this and maybe this. Write it like this, but not like this. So you can see why intertwined with each other. Another interesting and I think this is an important property of scalar product is that we declare a vector, and this is again more mathematical. You guys know what I'm talking about in mathematics. If not, don't worry, you will eventually do it, and this is important for the example. But if you talk about vector A, then the vector, depending on which space it occupies, can have several properties or several Cartesian components. Come on. For some reason, it's not working anymore. There we go. This is the worst thing about this software, applying. There we go. Such as of I plus a j. Does any, when I say I and j, these are what they typically what do you call it? The name? Unit vectors of the x component, and this is the unit vector of the y component. And the interesting property of scalar product is that if you take a vector of A, B and multiply it with each other, you don't really, if you have individual components, you do have the x and y components. If you multiply these two vectors with each other, the interesting is that vectors that are of the same species, meaning R and I, will multiply to create vector 1. So AX times BX, or in other words, let's write it out like this. No, not the eraser. BX of I will be AX times 1, meaning that it's AX BX. If I take I and multiply that with y of j, then I will get AX y, but that will be multiplied by 0. And that is simply because the angles between those I between, you'll notice that the angle is 90, and cosine of 90 for anything that is orthogonal to the other, they will out, producing 0. Or if parallel, remember what we talked about with force. We said that in the same direction as the distance traveled, we only consider that component. We excluded the y component of the force and just took the x component multiplied by the distance. This is what we're essentially doing. We're essentially establishing here is a scalar product. And so this is so it just so happens, but the work, we can determine the work using principles or the of scalar production. Just as we can. This is a very simple explanation to what scalars are. I know it wasn't what I just explained, but just if you know this and you know how to vector equations and you know how to multiply as a result. So by here, this times this will evaluate AX times BX, but this will equal a value of 0. I is 90 degrees. So we're talking about essentially vectors placed when you do in a scalar product is okay. Explain the scalar product. Do an example of a small size of. I'm going to save. No. Hold on a second. I should have put a new image. Hold on. There we go. Now undo. It's like watching time. There we go. I'm going to as scalar product onto desktop. Okay. Let's do our first size, and then we can move on to a bit more interesting. We have two vectors, A and B. Actually, click them. A is a vector, and don't worry, we'll make it bold and it's a vector meaning 2i plus three, and B is a vector meaning minus. No, I'm just going to zoom in some more. Minus I plus 2j. And I just want you to find this too. I don't want to solve this, so I'll give you guys to solve. Just E is bold. A is bold. Yes, I'm very important to answer very quickly. Maybe I'll solve it immediately as well. I won't wait for you. What we're essentially doing is creating a multiplications. There's two ways of either vertically or horizontal. Keep it horizontal for now. And minus plus 2j. And we set terms same direct, but in this case I and I will also be vectors, by the way, but I can't remove all. Actually, maybe I should, just in case you guys get confused. So this didn't work out perfect. That's supposed to be 2. Okay. So now that we got everything, 2i times minus I is equal to minus 2. I'm assuming, yes. Just double checking, yes. Will yield in something that is, actually the first way we do, say for example, 2 times 1, and then we also look at the i's, and we say, okay, these two are both in the same relative direction, and therefore I times I is 1, minus 1 is minus 2, so the first component is minus 2. Then we continue this like normal, or we could do this, but this might wait enough time for you guys. But you can also say 2 times 2 is 4. And you notice, aha, I times j is equal to 0. So I times j is 0, 2 times doesn't matter because it's 0. Part is, yeah, everybody's writing down 4. Down, and then we say 3j minus I, and then we could times minus 1 is minus 3, Then we realize j times I orthogonal to each other, and anything orthogonal will yield in cosine 90, giving us 0. So we just can ignore these two, the multiplication of these two, and then say 3 times 2 is equal to 6. So then we write finally the second component of our equation, which yields, which is equal to 4. If anybody got anything other than, please practice your scalar product. Basically, algebra with steps. I think just to make sure I get it very quickly, I would like to find the magnitude A and B. This is something you're able to do. Find the magnitudes of A and B. I'll write them down. Just write SQRT and whatever the answer you want, like this. And I would like you to find an angle between A and B very quickly. So you can give your answer action or. And in the meantime, there's exercise 2. It's not really much of an exercise. Very good. So Ali Reza, so I pronounced that correctly, is giving me the square root 13 square root 5, effectively for A and B. Is 100% correct. So the magnitude of A is equal to, and I'm going to have to write like this, but just for anybody coming, this is root of A squared plus y squared, and the same stuff for B, so I don't want to waste too much time with that, which is equal to square root of 13. Wonderful, wonderful, wonderful. So the same procedure we're going to do in B, but I don't want to repeat all. So we get square root of 5. The same step 4. Thank you. Can you tell me what the angle is between? It shouldn't be. I'll just write it sine theta. You don't got theta. Where is my? Give me my symbol. Is equal to the product. Another way of looking at it. Okay, people have already given correct. We're glad. Divided by B, which is basically a reformation of the rule I gave you guys in the beginning, which is A dot B is equal to AB times cosine theta. Find the cosine inverse of this, and you're basically good to go. So theta is equal to cosine inverse of sin and yield of 60 degrees. So hopefully this clarifies everything that you would in other products. If this was an attempt to lecture, good. So about more exactly point, we always want this enough. No one cares about the second small place. Is it 6? It doesn't matter. Right, 2. Okay. Have you guys done with Deagle concerning work? Because you guys should do at least iterate or under a curve or under a curve. Yes, a long, like a long time ago with Deagle, or a long time ago you mean back in high school? Because yeah, at the beginning in school, I did not learn. Oof. Okay. So, do I want to open up these cans of worms? It's going to be a little bit difficult if you guys, because we should be starting with work energy theorem, or kinetic and work kinetic energy theorem. And I think for that we definitely need to understand what an integral, or how to determine work using an integral. Okay, let's create a very simple, oversimplified scenario. First, let me save this. We're gonna make a very simple scenario here. We'll take our little beautiful square. Bam. No, I'm kidding. We're gonna take a little square here. We're gonna insert some colors around and inside it, have it with add a beautiful gradient to get a fake perception of 3D-ness and what is, by the way, they are bricks to you when you ever make your figures one. Just add a gradient to everything. It's a little bit prettier. Anyway, and then we take a force and we apply it to the center of mass, and this is thick. There's an arrow pointing to the right, and we can define the force as being something 50 or 5 newtons. Okay, and we're going to move for a distance x. What that means, we're leaving a variable in it, and we're going to see what happens after we do change. We dig the scenario so far. If I now to translate this information into information, a graph. Let's hope we can way. Oh. Okay. These are the two x and y. I know x and y, but we're past this, right? We talked points because somebody x or y. I think at this point that this is y and this is x. Please somebody complain. And let's ignore next because we don't need that right now. And let's of our system, which in this case is just a square or a block, and let's assume that the system as the block with a constant force of 5n the distance x. What we do not know. So what we should see, if this is the case, already it means there's no acceleration, increase in speed. We should observe. Actually, now I put. and this new that came back to bite. So if we look at our diagram, we'll push this down a little bit. There we go. We can see that as long as the force is the distance of x increases constant as well. Can everybody see? So if I have a force of, and this is of course the force I was talking about earlier, let's graduate our diagrams over here. Of course, not perfect, I know, but it's we do for now. And we can see that over the force applied to the object distance respectively doesn't, there is no sudden or sudden decrease in the distance, as long as the force is constant, that continues. So let's, from this point, I want to determine the work without using the classical equation that we've used so far, which is 5 times whatever distance is here. Rather, I said, you know what, I'm not a big fan of this simplification. I want to use some Newtonian calculus instead. Well, another way of looking at the diagram is to pick the little rectangle, little rectangles that are beneath the text. If you guys know simple geometry, you can actually already solve the answer without me really demonstrating the exam here. But this is actually the base calculus, what it means to integrate. We can imagine that they're underneath this line, and these rectangles have a number of, can either be 5 rectangles, they could be actually less than 5 rectangles. We can reduce their dimension even further, pushing them down more, so that maybe for each rectangle there are 10 rectangles. Oops, that didn't look pretty. Okay. Oh no, we're not going to do it like that. Let's do this. Okay. So now we have more and more rectangles underneath. This is actually the principle behind integration. When we talk about integration, talking about the theoretical trapezoid of trapeziums underneath the line of interest, and they approximate the line as close as possible. So when he was bored out of his mind, is that he said, let's imagine that these rectangles were infinitesimally small, that they represented the smallest unit of x. What does that mean? We don't know, because pushing a dimension into another dimension seems kind of ludicrous. But he said, you know what, we just want the closest approximation as possible, and we're going to create this value called infinitely small. That means that it's unperceivably small, or the smallest unit possible for that thing, which is x. He just called simply x. And he said, for the instance of dx over where x exists, over length of x exists, we'll multiply that by f. And now I got to whip out my Greek symbols. Integral. There we go. Hopefully this will work. Perfect. He said for a between whatever area of interest, area that we're interested in, we're going to multiply this length of x, this very small length of x, by force. And slowly you guys can recognize what's going on here. This is essentially a fancy summation function. It is almost similar to, but not exactly to, writing this. Which is the sum of times the smallest, which is essentially what we're doing. We're these little rectangles up to the point of interest between 0 and wherever this distance be. So if we were to write an integral, okay, nobody's anything, then I would write something like from the distance 0 to distance 1. Not 1, let's say 5 meters. So my question to integrate, well, okay, you just, I don't know if you guys have done integration before, assuming maybe a little bit, but hopefully you guys know how to integrate. Can you integrate this thing? What's the integration? No, nobody? I'm going to count to 5, 3, 5, or down from 5, 5, 4. Okay, there we go. Somebody wrote it. It's simply f of x. So after we integrate it, we're still not done. We still have to subtract the area of from the starting point of the area of interest to the end point of the area of interest, which is going to look something like this. And then you guys start to realize, it kind of looks like we just rediscovered the wheel. We're essentially we found another way to derive work done using another method like calculus. Yeah, that's the case. And I think the more ways we have, we can more are disposed to us. And so this becomes 5, 0. It's a little bit unorganized. Which is 5 f meters of the units. Come on, sorry. Actually, we could have simplified this. And that's equal to 25 Newton meters, which is to joules. You know that. So what we've done here is found another way to vary underneath the graph. And in this case, when we have a graph of the force and distance, area underneath the graph representative of the work done. Now, this was an overly simple example. I think you guys needed an integral through this. This was actually, in my opinion, more of a waste of time and benefit. But there are cases where this is not as simple as a square. Before I'm giving you examples of fundamentals, where we're talking about simple forces applied, like F. But what happens if we start doing F? Well, there are methods to approach the solution. Let's assume I got really tired And now what happens is that my force drops starting at, hold on, let's try to make this. Now look what happened. Now for the student here who will go like, oh, sir, I could just look at this diagram, laugh at your face as I take a line from here to here. Oh, this doesn't align it properly. And separate my diagram to two geometric shapes. Well, I would say, good for you. That's not the goal of today's or of this current lesson. I want you to apply a form of integration to this. We have 1, 2, 3, 4, 5, 6. So all the way up to 6 meters. I want you guys to find, actually, let me double check this. Can you guys do this? I think you can. But I don't think you need to use it. But we could use it. It is principally the thing. I want you guys to, with whatever method you got, the work done is in graphical presentation. What essentially is done here is we've gone from a point of X from a graduated line meter. So just here, this is 1. And this goes up to 5. Actually, let me simplify it for you guys. Make this go to 4. There you go. I want to run whatever the answer is. I think pretty much going to be very similar to what we've already done. But nonetheless, I'm to see. Tell me which method you use to underneath the curve. You split it up into geometric shape. Did you use integrals? What method is applied in this case? And just to clarify, the diagram from before, the object constantly with a force of 5n, but as we move up to 4, my force begins with it the amount of distance, obviously, and drops down near to 0. And Mbam answered already. If there's any, okay, Mbam split it. Everybody else who are not concentrating, but hopefully they'll return. Ah, you guys can put ticks up there. I want to correct it to 25. Very good. The answer is 30. Okay, somebody said 30. What else do we got? Oof, 35. Next guy's going to say 40. I'm going to, oh, 35 again. I'm curious, did I make a mistake in the presentation? No, I don't think so. Maybe I made a mistake, but I think if Bill got 5, can you explain to me how you got 30? That would be wonderful because I am only 35 at the moment. It should be 35. some people are getting 30. So let's maybe solve this together because a lot of guys are getting this wrong. Maybe it was my explanation. If so, I apologize. But the simplest way to look at this would be first to talk about putting it into geometric shapes. We can, and I think this is a little bit of a risk. If we split the object into parts, then we have times 4. Wait, 5 times 4, which gives us an answer of 20 joules in the first part. And in the next part, if you guys just took 6 times 5, that would be definitely wrong. Or if you could probably take, some of you probably took times 5 instead, right? I see where, okay. Guys, come on. Triangles, what are triangles? So those who answered 30 subtracted the distance of 6, which was correct, multiplied it with 5 immediately. Give an answer of 10. The total work done would be 30. This is incorrect. You have to take into consideration the sheet that you're working with here. This clearly is constant force applied. The force is varying. You have to look at this as a decreasing force, the distance. And the way you can do this is either integration, where we realize that, okay, the gradient is such and such, a triangle, grade, find that area underneath it. We're simply say we're working with a freaking triangle. So if you find the area of this equation, look at the area of triangle. I don't ask. Just need confirmation of very good. So the half base times the of which, so the half needs to remain. The base is, now if you put in 6, you're definitely wrong. So the answer has to be, because we are only concerned with this, which is from 4 to 6, which is -4, which is 2 of that, and the height should be, so this is of course, this is newtons. And that gives us 5. Making the work done over this distance, 20 plus, I hate this, 20 joules, 5 joules equals to 25. Is that clear? Just send me one of these if you could, like that little. Actually, I'll just say yeah. Let's just find a way. Yes, it is clear. Very good. Bob says it is clear. Yes, sir. God, we're back to that soon. Okay. How long have we been at this? An hour and a half. When does the lecture end? Oh, trickery. What time should be like 3 hours long? I think now. We have a 15-minute slot. Okay, then I think a 15-minute break now, and then we'll re-adjourn in 15 minutes. So about 10:20, I expect you guys to be for the second part. And then I'll still be here if you have questions. I'm not going anywhere, but it's on break for the next 15 minutes. someone can copy it in the chat box, and as a return, I will answer them. I was talking about, I don't know if I can send a file here. I think, hold on. Let me see if I could just send it to you here. But I sent it to Diego, and Diego should have sent it to you guys. It's a script. I think you uploaded whatever online system you're using to information with each other. I don't know if it's Elias. Yep. Was the Bericht. There we go. Oh, yes, we have. Okay, good. Good. Did you feel like it was full? Very good. Perfect. Do you find this way better good? Does it suit you? How do you feel the pace is? It's important feedback for me. It helps so I can adjust for the next time at least. Okay, so I hope by now everybody has returned. If you are currently present, please just write here or find another way to indicate your existence. We just been talking about how to apply force distance diagram in order to work done is, and the work done is the area graph. In most cases, it's really simple to determine if the graph, the cases that I've given you, if the graph is something that's geometrical, something that you separate into a square or a triangle as shown previously. However, in most cases, it's not simple. Maybe I just want to give an example very quickly without solving it, maybe something for you guys to do on your own. But let's assume we have an axis here. And we, excuse me. Oops. Somebody talking? I just realized I forgot my from here. So whoever has the microphone on, that would be ideal. Okay, I think but now the case, we don't have geometric shapes, something more elaborate, tricky, sneaky, whatever. Actually, not before I do that. This is still not a very difficult geometric shape. Oh, that's purple. There we go. I think most of you are very this more or less. It's not the sum ever. It's just an approximate Please forgive me. So most of you should recognize this function. Of course, the x and y axes. Let me try them with their appropriate arrows. And let's just assume, for the sake of argument, this x represents, actually, let's just pick this guy. This x represents x in meters. And this represents in newtons. Oops. So the question to you is, know what this function might be, which hopefully represents to some extent a parabola of a quadratic function. How would you determine the area from 0 to a distance, or not the area, rather the work? Let's call it work. Whatever. Using your understanding of previous, how would you determine the work done from 0 to 2? Right? That's a question that some asked of you. It, of course, is again a linear curve or quadratic curve. It's linear in one sense, quadratic in another sense, but quadratic function. And we could represent x is equal to, here's something unmuted microphone. If you are on this server, please mute your mic, would be ideal. Thank you. Then you can represent this as, sorry about the delay. You can represent the function, this parabolic function as f of x is equal to x squared. Of course, it is starting from 0 onward. So my question to you is, knowing this information, how is work done from 0 to 2? That's my question. You guys are going to, I'll just turn this into a, like that. But that, of course, will be an estimation or an underestimate. What? I want you to find the area of this curve over here. That's my question. Is everybody confused about this? Gave me the right answer. But is everybody else with this? We can't see each other's chats, I think. Okay. My apologies. No, Mbam, your chat can be seen by everybody. It says Diskussionsteilnehmer. Tirt can also send this on everybody. The thing is, what we need to do here is, if we want to find the work done over this amount, over this distance with this kind of a force curve, and we know that the function, the force relative to the distance, is a function of x squared, then we can perform earlier with the integration. I say that the integration W is equal to integral, I need to get that again, of f of x dx. Actually, no, that doesn't. the area under of f times, sorry, okay, of the function f x, so then we determine that, like, we determine that area underneath the curve, and we in the chat said you got the right third. If you could elaborate a little bit, that would be fantastic. Hold on one second. My apologies, okay. So we can, wait, hold on. So we know that the function of, okay, the function of f, my apologies, now I got it. Okay. I mistakenly called this a function of small f. It's of course the function of f that is our y, dependent on x, and we know that it is equal to x squared. There we go. Oh, I thought I did a mistake there. My apologies. So now that becomes the integral of squared of dx, and we know that this of which is 0 to 2. So that should equal to, you guys know how to do integration. If not, don't worry. If you don't know how to do it, that should mean you don't need to worry about it, hopefully. It's cubed over 3, which equals then to 2 cubed. There's one information missing. Range. Let me write that. So it should go from 0 to 2. And in this case, after we should also have it from 0 to 2. And then that should give the power of 3. We don't need to that a little bit. There we go. Don't need to consider the 0. We 0 to the or do we know we consider the 0? Because 0 to the power of 3 is no, we don't need to consider 0. And divided by 3, that's equal to 8 over 3 joules. And planes that I forgot to get, I apologize. Oh no, wait, I'm still missing. No, I think we 8 over 3 joules, and then should work out fine because we're going to use the curve. Okay. The answer is 8 over joules. This is integrals, integrals are the integration of x of dx to do work done over a certain. This can be expanded in satellites. I don't want to do this for example. That's a real headache integration. But this is the you should get in the end. Okay, with that, I'll move on to because I don't think we have to and discuss very briefly springs. Did you guys law? Quick yes or no? Anyways. Oh God, nightmare. There we go. 2. I'll just do 3. We're gonna call it one. So you guys did do but let me rephrase the question. Did you guys do Hooke's law? Diego? Let's put it that way. No, system. Well, this is, I don't, so, okay. Okay, we're going to talk about with elastic objects, and in order to do that, we need a very simple Hooke's law, which states that the force applied to the spring is proportional to the disk move times some constant factor of that spring. This is a very typical linear equation. Sorry. So let me add an object. And please forgive my terrible. So Fs is the force of the spring. That should equal to minus K of F. What is K? K is a constant that is, okay, that says, yes. I'm going to explain it very briefly. Get a refresher. The spring has a property, call it K. The spring constant of a in physics jargon is the distance that the spring moves relative to some null point. So if, for example, I move, represent by null in the organization of energy, this is now my system. This whole thing from here to here, that is now my system, that is my frame of reference. Just to repeat what we talked about at the beginning of the lecture, what it means to have a system. In this case, this is now my system. I did forget to draw, otherwise it looks like that they're suspended in air, which is not the case. You guys should have also, right? Please tell me, God, tell me the friction. Okay, so if I represent point, null point, just in case anyone is confused, here as my null point, which is equal to 0 at this. Can anybody tell me how I would determine the force I moved, or what the force is if I move the object to the right 2 meters? If I stretch it out by very quickly, and assume K. Let's keep it that simple. So the property is K is 1. I stretch out 2 meters to the, wow, 2 meters. Moved it out to, what is the force that I apply? Keeping in mind that is 2 newtons, yes. And now this is interesting. I think I have to mention that the spring constant, just so that everybody understands where the unit is coming from. Very briefly, I need to say that the spring constant is a unit of, in meters, just in case anybody wonders how we can get a Newton from this equation. So it is a constant, but it's a constant with unit. So it's not just a it's a proportionality constant, what they call it. 2 newtons, 2 newtons, 2 newtons. Very good. Took into consideration the direction. I'm assuming. And now the question to you is, I compress it, then you get the direction. I don't need to do this for too long, and I move it that way. The fact that the 2 is now inverted, 2 meters that way, then like a force, yada yada. This should be, I don't think I need to for too long. What I want to talk about is the graph that resultant from this experimental. That gets a little bit more interesting, and the more we can find more of this integral ideas. Sorry, I will say integral ideas into our So you said if I move S is negative. Oh yeah, by the way, no wait, I think I made a mistake. If I move it to the right, Fs is negative and Fs is positive. Okay. So I think one thing that you guys need to correct from your previous calculations is just the negative sign. But really, at the end of the day, it depends on what frame of reference we're taking. This always happens. Okay. So we should have a diagram that looks sort of this. And on the right side here, we have is x in meters. This is of course assuming that the spring behaves very linearly, which it is, and so in most cases, otherwise. And we know inherently how when we spread, at first compressing it relatively easy, the more I have to move it, the more the force is required to move it a certain distance. I believe, yes. And so it is at my null point defined here, I have a representation that looks like this, and I need to then, as a result of the area underneath the graph, I want to know how much it is to move it a certain distance, maximally away from null points or minimally, or as far as on the other side as possible. For example, in this case, I want to know how much it is to move it or to compress in one direction. And let's say this is over here a certain x, we define it, we call it x. We can determine the work to move it to this point. What is the work done in this case? The work done is how far I can move it, and that's 2 meters, which would be a lot, which looks like for a relatively spring. And we know that for, hold on. What this line represents k times maximum distance of x. Can I make a subscript? Oh, God. I think I can do it like this. And I can determine that the area underneath from here to here the area is 2 0.5 speed triangle times square. I need to write something. Can But everybody understands the importance. If not, please say. Well, I just either. Okay. Okay, good. This one person understands this so far. Angie. Okay. What can we do now? We've talked about spring. Edie Adiga is back. Hello, Professor. Good to have you back. I'm assuming at least. He's on the phone, I think. At this point, I would like to maybe do an exercise concerning measuring for spring. Or we should jump right into kinetic energy theorem. I think we'll do one exercise of the spring. I don't think it'll take that long. But if you have any questions, please read it. If not, let's do one exercise concerning and we'll work done. Other than that, we will move on to kinetic energy and the work theorem. So let's look at a surface or ceiling, and from that ceiling we have ceiling. From it a bolt. And what we want is if the spring is 2 meters, what is the work? Spring stretch to. Okay. Of course, you need more information. It's nothing yet. Lower end action. Oh, the spring stretching. Okay, so there is a load on there, and that load is from the bearing itself, which we will not. We'll just simply call as n. But result of this force, it is moved down to 2 meters. Until equilibrium. The mass of which 55 grams. Oh no, kilograms, sorry. And so the spring is stretched by 2 centimeters. What is the constant force that is applied to this spring? Is I think the first. What is the constant force? Meaning not this force, but rather the force of the spring that is applied to this. What is the force that is applied to the spring as a result of this load? Is my question. So what is essentially Fs? Shouldn't be too difficult. This is sort of a mixture between what we've done in the last lecture I gave you guys and what we've done today. So type here, and in the meantime, I'll write out the second question. So A is F for Fs, and our problem B. So is that clear? The questions to the problem? We're basically as for the first, okay, not bad. Serge says, oh, okay. We're talking about K, right? Oh, there, Serge. Serge? Yeah. 5.5. That's good. So I think you can for. Okay. Good. Very good. So let me ask another question. I think because it's a little bit tricky. I purposely left out one piece of information. What we're asking in A is not really the force, because we know what the force is. We know that the constant force applied to the spring is in fact the load. So what we should have done initially is assume a free body diagram, not assume, make a free body diagram, and we have to then immediately go like, oh, I've seen this, or Sir did this. Well, I did this last. We talked about free body for hours. Right? And we know from this, without text being upside down, it should equal to this spring force. Oh, let me set that over. Right? So we now can say that the spring force is equal to mg, and in fact, we could immediately determine what the force is if we just determine what mg is. But I think what's more relative for this B section is that we need to know what this constant, this proportionality constant is, this spring constant A. So we say that is equal to whatever distance, in which case is 2 centimeters. We start creating a equilibrium. We will state that, sorry, let me write that. This, due to the equilibrium, we can determine that K is equal to mg divided by whatever distance. We call it d, we can call it x, we can call it herb, whatever it is, it's definitely 2 centimeters. The reason we avoid using maybe x and y too much is because we don't want this just to get confused. Everything has to be either in x direction or direction. So I think using term d and r might help alleviate the situation. So we can determine that K, hopefully we have determined K as a result of this, is equal to 2.7 times 10 to the power of 2, and we call that newtons per meter. So hopefully you were able to determine K, the body diagram and understanding of elastic energy. And now let's move on to N. I'll put the A down here. And now the B section is how much work is done by this stretch centimeters. Well, we can either redraw a graphical representation of this and determine, or we or accept this as a constant as long as it's linearly. We can say, well, I don't need to always determine what I don't always need to triangle to determine what the work done is. I'll simply say that the work done from that graphical representation which is my null point, minus 0.5 times KD or k at whatever square, which is the distance. And if you've done this way, you'll find out that the work is equal n, I believe, to what k is, which we determined to be 2.7 times 10 to the power of 7. So it's 1 joules, all of that. If you take 0.5 multiplied by k, that should equal to hold on, we'll half that away, that remains, so that should minus 5.4 times 10 minus 2 joules. You could have be a little bit smarter and call it centijoules. Nobody does. Nobody calls it joule. Nobody centijoules. It's just weird. So we'll just take our minus 2. Is that clear? Hopefully, I'm hoping yes. Clarified how it works for an elastic object, more particularly. Questions so far?
I don't really understand the B part. What you did exactly? Yes.
Is this I know you have the power for some reason. Unmute yourself.
Yes.
Or actually, since you're here, just tell me what exactly is it that you don't understand, and I think would be a lot more efficient.
Because I'm seeing negative signs, and I don't really understand why.
Because we're starting from a 0, and we are. Okay. So your question is why there's a here probably, right? Why is it not the other way around? Because what is the equation for the force of the spring? What do we take it? What norm for it?
The spring constant times the extension.
Exactly. So it's minus k times x.
Yes.
And so when we apply, oh wait, hold on a second. No, now you've confused me. Let me double check something. Yeah, that should be. So then we start off at an A point. So okay. So if we extend, things move in the positive direction. No, it should be negative. Let me double check that real. If we move towards the point, I'm assuming my null point is move towards my null. Okay, so it depends on where you define your null. This is the thing. I think typically we can say that we can, for example, in this case, go from maximal compression, which is, I think, what we did. We go from maximal compression. So I'll take my string here, compress it as much as I can. Hopefully this also helps things like that. And I will define my point here, so that if I move in this direction, the resulting force should be from the start. Check the start should be positive. When I apply my equation from to the yes, the resulting force is positive. Therefore, the work done initial phase is 0 because it's moving. And once I move closer to here, then I'm subtracting the work done further along the way, and therefore the resulting or the end force applied should be negative. That makes
what if
it's all relative. That's the most important thing you have to understand. It's why is KD squared just real quick, let me refer to if you remember the diagram we did. Let me see, save and then go back. I'll get right to you. but I think this is an important point. KD squared is then I think that it does. So here, this is why KD squared. Remember, we talked about earlier that if we find the graphical representation of the spring, we can use area underneath to determine the work done. And we realize it is 5, which is the area triangle, times the linear capacity constant times x squared. So hopefully that explains that. If not, class I would on. Oops. Back to question regarding.
I want, because you said that it's negative in this case. What?
Oh no. Oh God, sorry, I'm sorry about that.
What if the string setup is upside down, such that you're pulling it upwards? Would it then be what?
It would depend on where you define the null point, at which point you define the system to be the distance to be at 0.
Yeah.
Does that? So if let me just my inks again so I can draw for you. Oh, that's not how I'm doing. 250. Let me start sharing the screen. Can you guys see that again?
Yeah, we can see now.
So, example, I have 1 second. Let's take that rudimentary example again. But in BAM, I do have to move on. I do appreciate the questions, but I do have to water. But I do appreciate the question. If it's not clear, I will clarify it hopefully after. Okay. If I decide, so this x thing, about this distance thing, it really depends on I define x0 to be at. X0 to be at a point, max the compression is at its max. That, but rather like this. Kind of like, well, right? I could do something like this, and then I could say x. And once I release, any distance that this load moves as a result of this is everything on x0 would be if we had the maximum compression located at. Right? So if I'm moving to the right, this is then in how we determine our frame of reference. And if we apply that equation f of s is equal to minus k, then we know that if we're in the direction, the force of the spring should be negative. Does that make sense?
Yes, I understand now. Thank you.
Okay, good. Thank you very much for your question, Imba. If anybody else has any other questions about the string, we can ask me afterwards. Hold on, let me mic up again. And then, Bam, if you could please do me the favor of turning off your microphone. Thank you. Okay. So now that we've discussed these types of, what do you call it? Or types, or what am I looking for? What's the word I'm looking for? That we're looking at methods of solving the work on a system. We need to start discussing, first of all, what is this? What relationship does work have to energy? Why distinguish these two? How are they related? These are all questions we should answer before we start with kinetic energy theorem. But maybe before that, as a startup, we can talk about different of energy. One that we could define as energy might be, we could call work energy, but that would cause more confusion than reassurances. Work we can more clearly imagine as a method of transferring energy. So if I grab this can and I'm across the floor, when I'm performing to it and as we're transferring it, to this Coca-Cola can to move it. That is what work is. It is in the units of the same unit of energy, but it is not necessarily energy. I think that's one pitfall that a lot of people get confused. Another are heat. A lot of people would like that heat is. I even use this as a beginning as a way to describe form of energy, but it's actually another form of energy. So it's another form of imagine. How would I explain it? It's a mechanism of energy by temperature. I can describe it. So you touch something and you feel heat. What you're feeling is the heat the temperature change transfer your fingers. That's why, because something feels hot doesn't necessarily mean it is hot. That just means that there was a or a sudden change in temperature of changing temperature. Another thing is mechanical. Those are very interesting, a form of transferring energy, and it's for things to problem mediums for water and solids. Sorry, I'm sharing my. At this point, we don't really need it. Where's so very common mechanical energy is that musical instrument in the background that is a vibrating and is a form of waves. But these are discussing all the question is, then what is energy? And that's an interesting question, because I think what it boils down to is a very abstract idea of something being within a system, and that abstraction is transferred through means such as mechanical, as discussed, like heat, like friction, or work. Sorry. Hold on, guys. My apologies. Yes, heat, mechanical waves, and even electrical transmission. So let's put kinetic energy relative to work. Actually, before that, if you guys would like to take a 10-minute, I'll be right in 10 minutes, and I think we have about, and we should be back here. Can I mute the microphone? Okay. So as viewers are going to work, and I think the best way I was thinking about this, and the best way to maybe describe energy is that it is a property of an object, and this property is quantifiable. It has a quantity, and this quantity represents how much work can be transferred. I think that's the best way I can briefly describe what energy is. The question becomes, what does this relate? How do we distinguish energy from work? You can imagine work being a total overview of the amount of energy transferred during a system, an actual system. So let's take an example, a block again. I think this is probably the easiest part. And we take this block, and as done before, moving this block with the sum of forces one direction. I'm going to represent this one vector. Oh, I need my alphabets again. As the summation of forces in direction one second. There we go. So you can see it. And we make this block X. Oh, whoever's joining, please mute your microphone. Always when you join, immediately mute your microphone. Thank you. And when we move at a certain distance X, we can determine that work is the sum of forces times X, and we did an integral over it. But this time we're not talking about one single force, we're talking about a summation of forces. That means more than one force applied. And if we want to find out what the sum of all work is caused by all, the sum of all forces, then we can determine this as in another work principle, which is my integral. Oh, come on. I gotta wait integral. As the sum of forces over this dx. I don't think we're talking here. The only thing I want to be that here from x initial subscript. Oh, come on. And here we're starting and ending at x final. So if we do an over area or over the distance more precisely, then we're at an integration that also occurs from xi to xf. Hopefully this is so far. Anybody has questions, please. Otherwise, I will continue on. So the question becomes, what is the sum of forces in our case? Well, we know from Newton's second law especially if we're talking about direction. We're talking about, hold on, there we go, equals to mass times acceleration. This is the Newton's second law, and we know this for a fact. We've done this in the previous lecture. This is, of course, a vector and a vector in this case. Let me make sure that that's clear. However, since we're working with one direction here, we can ignore the multivariate directions, just concentrate on the one direction, which is acceleration in the direction of motion, which is in this case. So we can change this back to an italic and talk about x alone. But this is self-evident, I'll simply call M8. So now that we're working with rewrite equation, we can rewrite our equation. Oh, it didn't take the excess. And A of dx with that summation, because we're only concerned with forces in that direction. And M, of course, here refers to the mass of the that is being moved. And we know that rewrite, now this, do you guys know that you can rewrite acceleration as a derivative velocity? We want to convert this equation into distance. You guys did this, but I'm going to quickly so that you guys know. You can write this as the derivative of speed time or velocity time. And you can then rewrite, extend it further, cross product, some form, 8 cross product. One sec. I'll rewrite this on the bottom. dv of dx times dx of dt. This is spin, or not trick, sorry. This is at, what do you call it? The same thing out very, in fact, if we apply these terms together, we'll get the dt form of backwards propagation. And then from there, any questions so far? No. Mathematics, we'll separate it. We're getting there. I think you guys know where we want to do anyway. We know that if we solve for, or if we rewrite our equation, and finally, from this equation, or for V, we get that the total sum of stuff is equal to 1/2, or maybe I should just write this, times the final velocity subscript. Actually, I can also m, so it's minus v of I. And if due to this equation over on the bottom as the kinetic energy of the final minus kinetic energy of the, oh wait, one thing, who can tell me what? The squares. So what we have here is kinetic energy of the final, the initial. So in other words, we write this as Kf minus Ki. And finally, we can also further down to K. Where are my numbers? So we did all this work, literally, to figure out that the sum or the sum of work on object, it can be determined the kinetic energy, which states that the kinetic the final energy minus the initial kinetic is equal to the work done on object. And here you maybe can start to meant with the statement earlier, work doesn't represent energy, but rather energy transferred. And in this case, talking about kinetic energy that is transferred from one point to another, from this point to this point. Any questions so far? If not, I'll do the first exercise with file save as. Kinetic work theorem. If there aren't any questions, I would like to point out finally that this is the kinetic work theorem, what we're talking about here. So the way that we can relay kinetic information into the sum of work done onto an object. If there are no further questions, or maybe here, it's important to keep in this kinetic work theorem, actually, it's commonly known as work kinetic. And it's a small, but I don't want you guys to look. So it's a work kinetic theorem. The question is, does it apply in all cases? I would say not necessarily. It only could work in a case where the system, where the change in the system is more brought about by a change in its speed and thus a change in its kinetic energy. This is not ubiquitously applicable. You can't apply this everywhere. You can only apply it in a system where the variation in the work done is to change the velocity and hence the change in energy. With that, I would like to start our maybe also last today. Let's see if we can beat the clock. If you have any questions, class, I'll gladly answer. My best capability. File save as exercise 5, I believe. We're gonna have a block. Again, I know it's like blocks today. And we're going to apply force. But we're going to keep in mind, hold on a sec. So I'm going to try to copy, yeah, I should be doing that. Okay, so is the question, a 6 kilogram block at rest is pulled to the right on horizontal frictionless by a constant horizontal force of find the speed of the block after it has moved 3 meters. I'll give you guys 2 minutes, 3 minutes maybe. I don't want to take too much time. but this is a very simple app. Keep in mind the crucial word here. I don't see answers because it's tricky. Okay, we got one answer in. Very good, Mbam. Very, very good. I think the first thing we need to do in order to solve this question is to determine what the work done is on this object, which will equal, which we've done already 1,000 times. Hopefully at this point, this equation is stuck in your head. The work done on the object is equal to F times delta X. I need to, we'll just, I like to do it pretty. Why do we use that? In this case, it's because talking about distance not over a 0 point, although it is actually 0. Never mind, I take it back, it's actually 0. We can just simply use X. For argument's sake, we'll put it 0. So we know that F, which is in this case 12 newtons, times 3 minus 0, that's 3 meters, equal to say 36 joules. And then use the kinetic work theorem with work, but we have all the, we don't need to say the sum of work. Work is equal to the difference in kinetic energy, which we from the question that the initial speed of the system is 0, and therefore we don't need to, we can just automatically say since at rest I is equal to 0, the elaborate starts from rest, I is 0. K, it is simply equal to K final. Once we have that, determine what K final is. And we know that it's simply 0.5 times V squared. This V is final, just in and we know that this should 6. Somebody joined again. The micro, why is it always 36 joules, and determine that BF is equal to, as Mbam said, about 0.5 meters per square second. Meters per second. Is that clear to everybody? Just write a simple, would suffice. Very good. If there's any part of this that will, and I will help you maybe after class. Whose microphone is on? Oh, there we go. Yeah. Okay. Is there anything? Did you guys do dynamic and kinetic and static? No. Did you guys do anything with friction? Okay. Because if you didn't do anything with, maybe a little to explain what's going on. I think you guys the force stuff. Okay. Let's do a question concerning the same scenario, or maybe I should open up the same scenario. And if we don't finish the question next time, I'll give it to you as for next time. And I will give you plenty of homework a bit more challenging because today's lecture, I felt the exercise was a bit too weak. So don't worry if you felt unterfordert, challenge today. Okay. So let's take a block. I'll save as 6. And let's delete everything. And let's make it look a little bit. Oh, oh, that's so much friction. Look at that. Okay. What I need you to do is to hold on. Okay. Exactly. The that we did previously. We don't need this. So we have a 6 kilogram block to the right along a horizontal force of 12 newtons. Find the speed of the block meters if the surface is in correct coefficient of kinetic friction of 50. So this you're able to know. And I think the best thing you should do, starting figuring out what the work is, a free body diagram. I'm going to give you 5 minutes left. Then I probably move the home territory. But maybe so that you can get a head start on your home. What's important is that you guys first making free body diagrams. If you don't start with a, you're going to have a bad time. So we have a horizontal force because we have a frictionless or a friction-full surface. There's going to be a force of friction. To determine what this force of friction is, you need, of course, to know how to determine friction. Information that obtained Professor Deagle. Does everybody know how to determine friction? Okay, good. All the information should be there. So, whoa, Mbam got the answer, and that is constrained. Find the speed. Let's see. I think you may have. How did you get 2.45? Let me see. So, Mbam, your answer is not correct. It's not 2.45 meters per second. But you're a little bit off. I don't know why you're a little bit off. Like, not like significantly off, but it's not by too much. So it's either you forgot something, seems like more of a addition problem. I'm gonna try to wait up, talk a little bit, see if we can figure it out. If not, then we're gonna push it into homework territory. And for your homework, you guys think that what we took today, but a bit more, much more challenging. For example, determining how much work is needed to a coaster around loop-to-loop, because I think you guys did rotational energy or rotational dynamics. Okay, since we have a in, and bam, that's very good. You got it right. Congratulations. You don't have to do this as a homework. Use mass as distance before. Okay, I got it. If anybody else has any questions, I think then you've been in the lecture for today. I will be providing you guys with a script about everything that we did talk about today. It does take a little bit of time, so I do apologize for the delay. I'll try to get it done as soon as possible. Please try to solve this question now, then you don't have to solve it later. And we'll make it easier once you move on to the exercise plan for you. I hope you guys are enjoying the glossary that I'm Eddie does. I'll add it as well to our current script. And in general, you have any questions, contact me on my file. I'll give them here. Just call me Fosters or Hale or anything like that. With that, I would like to thank everyone for participating today. It's very much enjoyable for you guys, and I hope that I can get to do this more. What would be helpful to me is if you give back to Professor D so that I know how to for next time. Don't just keep in mind that criticism given on the Eagle is anonymous, so it's about me lashing out for something. Don't go anonymous. I appreciate any feedback given to me. And finally, please try to homework, because homework it will be towards more what Eagle expects you guys to learn from this lesson. I feel like we did today too overly simplified, so maybe a little bit too lax. If not, then good to know that I was able to challenge you. With that, I would like to finalize the class and hope you guys do the homework. I'll get it up by tomorrow. if not after tomorrow afternoon. Please do the homework. Thank you very much for your attention, and we'll see you guys in the room. Okay? Bye-bye. How do I start? Okay. If anybody has any questions, feel free to ask now. I'll stay here for about 5-10 minutes. 5 minutes, and then I'll leave. Students, computers, then if not, please voice if you have any questions. Best way to do this is to send it either by chat. I'll try to unmute the microphones to see. Nope. Okay. Well, anyways. Okay. Okay, it seems that everybody. Then have a nice one.
Thank you.